Oops. Yeah, the point is, I have to do a mental exercise to transform a linear operation.
Maybe you pass the slides.
Well,
Start in the meantime.
Okay. Okay.
yeah, I have to confirm, otherwise we don't hear it.
Just try to place where everything is and then take.
So it doesn't.
It's okay if it doesn't go, it's no problem.
Okay. It's not a minor problem. So
Yeah. Okay.
okay. So welcome everybody to another IAA seminar. Today we are so pleased and honored just to have with us to a very good friend first, and of course a very good professional. He has a very long career in development of instrumentation, Professor Martin Roth. He's retired, but he's now working as emeritus in AIP, Institute at Potsdam. And well, between his current duties, he's 50% supporting for astrophotonics and 50% supporting the emerging center, Deutsches Zentrum für Astrophysik. I don't know if the pronunciation was okay or not. Sorry for that. My German is not so good. But well, as I told, for us, it's a pleasure and honor because I must admit that he's a very good friend since almost 20 years ago. And he's during all this time, he's fully supporting all the activities we are doing at the Observatory of Calar Alto. And I think that we will always be in doubt with you. So thank you so much. Well, he's going now to talk about the ORCA-TWIN is a fast and low read noise CMOS camera project for planetary science and astrophysics. It's a collaboration that we want to establish for the 1.2 telescope of Calar Alto. And he's going to give us the detail for this. Thank you so much, and you have the floor.
Jesús, con mi pobre español, muchas gracias para la introducción. Es un gran placer estar aquí. Hace mucho tiempo que no estaba en Granada ni en Calar Alto, y entonces es un sueño en realidad de estar aquí con nuevos planos. Y para no volverme ridículo, déjame cambiar a inglés, mejor de hablar. It's, as I feel, as I hope you can see, it's a great pleasure to be here. And with us, we have already prepared some thoughts about what I want to address in this talk. Thank you for giving me the opportunity here in the room and also remotely. I see Ruben. Hola, Ruben and Jens.
Hola.
Connecting. I am the first time of my career confronted with an odd situation in that I want to speak about science that I'm not familiar with. So the first and foremost idea is to seek ideas from you guys, from the community, for a technical opportunity that has arisen in connection with the logo that you see on the upper left. DZA stands for the German Center for Astrophysics, which is in the process of foundation. And before I get started into fast CMOS detectors, which is the topic of this talk and their application on Calar Alto and elsewhere, let me say a few words about this new center, which may be of interest for you. Okay, go on. First of all, a view on the landscape will show you where I'm based, also contractually. I'm an employee of the Leibniz-Institut for Astrophysics, AIP in Potsdam. And in that position, we have visited Calar Alto. Actually, we'll celebrate 25 years anniversary in May this year in the context of the PMAS instrument on the 3.5 meter. And this is now a location right on the border to Poland, the city of Görlitz, where the German Center for Astrophysics is going to be created. It's in the process of being so. And I show you a few slides to give you an idea what this is going to be. The buzzwords on the upper left refer to research in astrophysics, to technology, useful for astrophysics, and digitalization, big data, that is coming from the focus of several of the research activities that are in the planning. But before coming to that, let me show you this picture, which is showing a coal mine, brown coal mine. And you have in Germany, due to the effects of global climate change legislation that was passed back in 2000, really worked so well. Back in 2020, the Kohleausstiegsgesetz, which basically stops coal mining altogether from the year of 2038, and maybe even earlier. And for compensation of the losses in the economy, the federal government has set aside a budget of 40 billion euros, of which the local state of Saxony, which is concerned, has decided to reserve a fraction, not only for investment in infrastructure, as you probably learn from the media, bridges are breaking down in Germany. It takes forever to build new airports, etc. Not only investing in concrete and steel, but also in brains. So there was a competition issued for 2 research centers, each to be funded with this amount of money, 1.3 billion euros. And in this competition, the proposal of astronomers was successful, leading now to the DZA. And the people who have been involved, first and foremost, former Director Science ESA, Günther Hasinger, and Michael Kramer for radio astronomy, Wolfgang Nagel for big data in Dresden, Matthias Steinmetz for optical infrared astronomy, and many others. They have done a great job in coming up with a proposal that was evaluated successfully in 2 major branches. One, which is related to the expected economic impact in the region, and secondly, on science. Unanimously, it was selected. So it's going to happen, and it's cast in stone. It's approved by legislation. Now, the concept for this institute is based on 3 pillars. As I said, astronomy, instrumentation, and this is my responsibility in an ongoing startup process to create an institute for technology. And then another big column, which has to do with treating the big data that we expect from experiments like SKAO and others. Welcome. Now, let me very quickly flash through a few slides without much commenting on it. One of the big projects, and you may be tiny ants, which are humans, in a big laboratory underground, in connection with development of technology of the interferometers for the future Einstein telescope. DZA engages in developing, for example, silicon mirrors for these huge facilities in a unique environment of a granite stock where this laboratory will emerge. Then I've just mentioned radio astronomy, the SKAO. Germany has become a partner last year. And in relation to this, the masses of data that will come in need special treatment with new technologies of computers. Now, for the advertisement, I have taken this jacket for this purpose only, if you allow me to take it off, because it's getting warm in this room. And then continue with saying a few words about technology development. The region around Görlitz is close to Dresden, and therefore, perhaps you know, rich with silicon industries. So semiconductor industries is very strong in Germany, in the region of Dresden, and also in the academics sector rooted. And therefore, there is mentioning of detector technology, CMOS, curve detectors, which are topics that are of great interest, for example, for the upcoming conceptual design of the wide field spectroscopic telescope for ESO, etc. So this is something that I personally engage in, also with research institutes like Fraunhofer in Dresden. As we speak, we expect a grant to launch this activity So this is something that should have great future. Again, to show you the locations, the headquarters of DCA is going to be in Görlitz, where there's a campus identified, new buildings expected to be built, labs to be created, and then a little bit remote from this in an area where they have a huge slab of granite, which is ideal for seismic reasons for an underground laboratory for the low seismic lab between the two towns of Filiación and Potsdam. And just to convince you that it's happening, we have already moved into a building as a provisional headquarters. And this is still mock-up, but the writing has appeared on the facade. This is where Günter Hasinger resides, all the offices are. And I'm engaged, and this is made up. This logo does not exist on the wall. In the rear part of this building, we have our first provisional labs. And it works again. Yeah, we had a celebration in January already last year with some VIPs, and I go through this very quickly because it's not the main topic of the talk. But to convince you that it's happening, we have laboratories that are indicated here. This is the more detailed planning, and electronics, optics, detector lab, more room. And perhaps the message that I will leave you with of this part is this is the staff development that was proposed, where we are now here in the first 3 years startup phase. Do we have a pointer perhaps? No.
That's a pointer, me.
Yeah, that is not so good. Yeah, I prefer a hardware pointer.
I think it's on the room.
But never mind. It's okay. I can also do it. Anyway, this is the end of the 3 year starting period, after which the institute is expected to be created. We have to go through an evaluation in June this year, and then we have already, with the stakeholders, agreed upon the statutes, and then this DCA will exist in reality. And this is the development of staff, where for the technology part, we expect to have at the ITE, Institute for Technology, around 270 or so people after a period of 15 years. And the budget that I mentioned is to cover this, and after that, it will be in the steady state. Okay, and here's a number of faces to convince you I'm not making up stuff. And oh, by the way, for the subject of what I want to concentrate on now, we have an opening. We will soon advertise it. It's very short now, provisionally, because of the practicalities of the grant. But if you have someone who has a PhD degree or even a master degree is sufficient, we could hire a scientist to work on the topic of fast CMOS for photometry here in Colorado. Please spread the word. I'm really looking for someone, maybe also with a routing here in Andalusia. And that's the architect's vision of the campus. All right, now I want to talk about high cadence time domain astronomy. Then I will focus on the subject of what is called QCMOS, a new technology that is enabling something groundbreakingly new. I will present you with simulations that I have performed recently to show what the advance is over current technologies, mainly CCDs. And then come to the ORCA-TWIN experiment that I am proposing to jointly conduct between DCA and Colorado, and hopefully collaborators here in Granada and elsewhere in Spain. And then just finish with a few trends that are becoming visible in the community. Since this thing doesn't work, I perhaps prefer to sit down, if you allow me to, and continue as if it was a remote. But please interrupt me if you have any questions. I can see you, and please raise your hands. Now, let me start with the first, as I announced, an area of pretty much ignorance of myself. Time domain astronomy is having to do with transients and short events, but not only. This graph that is from a paper in PASA by Burton et al. 2016 shows on a log scale of time So if you look here in days, you have the logarithm of time resolution that you need for observations for the subjects covered, and seconds on the upper level. And you see this is the second regime is really short. And then you have minutes like log 2, etc. So then you can see gamma ray bursts down to flare stars cover this regime of time resolution of minutes or hours, whereas some events point to very short time resolution, like fast radio bursts. And all of these activities were to a large extent covered already or are in the process of being covered by ZTF, the Weekly Transient facility on Palomar. And Caltech is very strong on that, but there are other facilities as well. And here's an example of the highest energy transient ever observed, gamma ray burst, where you see the gamma ray counts, millions of, and the short duration of it. To have optical counterparts observed then would call for very short time resolution, which is the topic of today's talk. Here is another presentation in a similar way. Katival is from Caltech, and by the way, she has visited us and is interested in a collaboration with DCA. So this should point you to the high energy interest of observations, where you have gamma ray bursts, radio observations, but then also the interest in optical counterparts. Here you have a collection that I've taken from a talk by Förster, where you see existing facilities. So here I mark the ones that exist for a cadence of 1 day on the level of hours and minutes. And we're now talking about the minute and even shorter time resolution, which is, as I want to convince you, enabled by the new CMOS technology. All right, just to remind you of two surveys, Kepler and TESS from space, where the aperture of Kepler was significant, 1 meter. The TESS is a rather small telescope, which will play a role when I come to an example that some of you may interest with regards to Carmenes and observations of M stars, where flares play a role. And here I just show you a paper that I've picked out, which studied the morphology of flares, however, just in white light. And obviously, the reason is to make a connection to the flares that we observe on the sun and the physics driving them. And if you look at the light curves, you see those peaks, which were here resulting from observations of an object with Kepler at 1 minute resolution. The study of those peaks resulted in a rather noisy appearance. And again, this would point, if you compare the different resolution that you obtain, this is now a test light curve from another object, where you see on the right-hand side, this is 10 minutes, where you don't see any details. Then moving on to shorter times, like 2 minute resolution, you start to see a little bit of the morphology of that peak and the details. And only when you go to several seconds are you able to see details of this flare event. And that's the point. And I have talked to colleagues in my institute in Potsdam who say this is very interesting physics. And they very much like to engage in making observations of higher temporal resolution with the 1.2 meter on Color Alto with a fast camera. And here's an example that unfortunately does not play for Color Alto because it's southern. AUMIC is an object that is known for an exoplanet, and you see the light curve. This is a rotational light curve with a period of 5 days, right? And you see the little trickle things. These are also flares, which are very disturbing. And the 3 areas of interest here are the ones that were known for an eclipse. The transit of a planet And you see here the light curve of the transit, which was pulled out of this huge amplitude light curve. You can imagine quite a challenge. And on top of this, the problem of flares. So it's the ingress and egress that determine the parameters of such a system. And my colleagues tell me that it would be very interesting to get to a higher time resolution of objects of this kind. All right. So I've picked another object again with no background knowledge. I've had a little conversation over coffee with Stefan with regards to asteroids, where I am using whether a higher time resolution can help. And here I found a paper that is about very nearby objects, low orbit objects, where you just can make with a CCD a streak image. And you see the wiggles here, they have to do with seeing and with problems of the tracking of a telescope. When we remember of seeing being if you go to time resolutions of milliseconds, able to show you the speckles where the image breaks down, and this must be the cause for such tracks on a long exposure. If you were able to break it down into shorter exposures, then potentially you could improve the accuracy of determining the position of such objects. And I find a press release from ESO, which is a nice example of observations of an asteroid near Earth, and we have this in the media. The next impact on Earth, probable or not. This is another object that was observed from Paranal, and simultaneously, again, a track. Well, I'm arguing it would be nice to break it down into individual exposures, but simultaneously, it was observed, I'm losing that, from La Silla, with an offset of 40 arcseconds. So I tried to find out whether this is interesting for direct triangulation, but Stefan tells me it's not a big point. Anyhow, if there are experts here in the room or elsewhere who would think that high time resolution for observations of solar system objects is beneficial, please let me know and try to use the opportunity. Now, here is the proposal. There is a camera shown in this picture that we have procured. It's available off the shelf by the manufacturer Hamamatsu, which incorporates the technology that I will introduce in a minute. And we have at AIP access to a 1 meter on Tenerife at the Stellar Observatory, which has 2 robotic telescopes, and there's one focus 3. But it would require some modification of the azimuth focus, including a filter wheel and a rotator. So it will take a little bit of time. But discussions with Jesus and Stefan have shown that there is already installation at the 1.23 meter telescope on Colorado, where we could probably in a plug and play operation put that camera that we have already in our lab, actually 2 of them. And this brought up the idea to have a installation on 2 sites, where the very quick one could be happening on Colorado. I have distributed locally a little collection of science cases and information. Whoever is interested, contact me or Jesus. Whoever would like to contribute or actually make use of such a facility, please send us a 1-page summary of your science case to be included in that document. Here is one example from a colleague of DZA. Thorsten Enslin is a professor from Munich who will move over to Görlitz, and he is developing a technique which is called information field theory, where he is doing, amongst many other things, image processing experiments that are 1 stage further beyond speckle interferometry that was developed in the 60s, which could profit from high time resolution and potentially then later on go to an 8 meter. This is one example, not necessarily science-driven in the sense of a certain class of objects or solving any problem, but this is an application for technology as well. So here's room for you to to engage, and please let us know. And in the discussion, provide any examples that you may have in mind. Let me now say a few words about this new technology. You probably have heard that what is available in our mobile phones is now taking over in lowercase SMOS, scientific CMOS, more and more. And industry tells me that the future has it that CMOS will probably rule out in 10 or 15 years from now CCDs. I've talked to Teledyne twice, and this is pretty much on the horizon. ESO, for example, is very concerned that CCD detectors may not be available for the next generation of big instruments. And we have held a scientific detector workshop in Potsdam in 2022, where this was already visible. There are still problems with regards to dark current, which was supposed to be an order of magnitude higher than with CCDs. And the other problem of the current available detectors is that the small pixel size is not making them ideal. But here's something that is fundamentally new, with some caveats still existing. So this is difficult to read, a table of parameters of the detector of this camera, but let's highlight the most important ones. So the number of pixels is 4K by 2.3K. Pixel size is small, 4.6 microns. So it's transforming to 0.2 arc seconds on the 1 meter. But the QE in the blue is really high, 85%. We don't have deep depletion CMOS yet. So in the red, you will see that the quantum efficiency at 900 nanometers with 30% is lower than what you would have with a depletion CCD. But I hear that this is something that may be changing with further development in the future. The readout noise, however, is the one that is now in the following making the important point of why this technology is so interesting. It's 0.3 electrons. And those of you who have read Jim Janicek's book on CCDs for astronomy perhaps have heard of the skipper principle. I've asked the engineer from Hamamatsu how they accomplish this low read noise level. When I started my career, RCA CCDs had like 50 electrons. Did you remember that? 0.3 is really almost an order of magnitude lower. CMOS, the PMOS CCD has 2 electrons. So skipper is a technique that is now coming back after an idea that was published in, I believe, 1991 by Tom Elliott and Jim Janicek, where the idea was to shift back charge between readout registers 100 times or so, and then make the reads on each individual charge packet, and then with the square root of reads, reduce the noise. The penalty being that it takes forever to read a CCD, like 2 hours. So it was not something for the normal applications. But we hear from Fermilab, for example, that with their experiments to find proposed dark matter particles, that they need extremely low noise. And this is why this technology is coming back. And the engineers did not object when I said, did you implant a multiple read scheme in your CMOS detector? And we are almost sure that this is allowing this to happen. Okay, and the other thing is that you can read this chip extremely fast. Unlike the CCD, which has its scheme of reading out sequentially rows and then the output register, each amplifier, each pixel has its own amplifier, and then there is a multiplexer in the readout circuit. That means that and you know that from the existing CMOS cameras, you can read much faster, and the frame rate is enormous. 25 frames per second in the low noise mode, and in the standard mode, 120 frames. So this is actually creating enormous amounts of data. So you cannot imagine to integrate an entire night, probably only on the interesting parts of the light curve or when a transient occurs. But this is basically, in a nutshell, the technology. And what I want to emphasize is the manufacturer is unaware that this is interesting for astronomy. And in fact, my research in the literature on ADS has found only one paper where this camera or predecessor to it has been employed in the AO system for Subaru. So my ambition would be with Colorado to bring such a camera to the telescope very quickly and publish first-off papers. All right, and why this plays a role for high cadence observations is shown in this cartoon, where you imagine a time resolution or time stamp, not resolution really, of 5 seconds. Yeah, you take a light curve with those slots to cover an event like the transient that we have seen in AOMEC. But then the real observing time, the real shutter opener, is only a fraction of those 5 seconds because the rest have to be spent with read time. And this is already an optimistic case of a fast read CCD camera. You remember the FIMA CCD reads half a minute. Whereas the CMOS camera from Hamamatsu has just 39 milliseconds reads. So the effective time that you can use for real shutter open time is significantly longer than I can provide you with the slides if you like. You don't have to take pictures. All right, and with that in mind, I've taken all the parameters that I could get from data sheets to make a direct comparison of commercially available cameras, namely the one that I've now shown with the QCMOS sensor, and an under camera with a Teledyne E2V chip with a fast readout mode to be somehow competitive. And then I simulated stellar images in a focal plane to be recorded with that camera with an IDL code. I have taken the telescope data to compute the plane scale. So there are various parameters that I will skip, moon phase, etc., sky background. And I've applied a Poissonian noise model for the star and a Gaussian noise model for the detector. And then from the resulting images taken experimentally, aperture photometry using the AOPhot, right, to get something that is objective. And I show you a few examples of this experiment, where on the left-hand side you see the CMOS, the pixelized image of the star. On the right-hand side, with the larger pixels, 15 microns for the CCD. And the circles indicate the choice of the aperture for the AOPhot, and the outer rings are the sky aperture for those who are knowledgeable about aperture photometry. And it's somehow cut here on the screen, but anyhow, you can see that this was taken with parameters for U-band exposure of an 18th magnitude star at seeing of 1 arc second. This was new moon, and the exposure time in both cases is 10 seconds. And then on the bottom, you see the collected number of photons. So after 10 seconds, you get 1,000 photons with the CMOS, with the CCD. There's not much of a difference, but the signal to noise is different. And why? Well, it's quite clear. The read noise of the CMOS is far superior to the CCD, right? And then you go to the V band and repeat the exercise. Now you have more flux and also more quantum efficiency. And you have 5,500 photons for the CMOS and 5,500 photons for the CCD camera. And the signal to noise, again, is different with the advance for the CMOS. And that continues on in the previous of the B band. I'm sorry, this is the V band. And we can go into the red. And for all cases where even now, where you start to see, because of the lower quantum efficiency of the CMOS, right, that the detected number of photons is only 3,700 for the same exposure time, whereas the CCD has collected 4,600, 1,000 photons more. But it's not the Poissonian noise that dominates the signal to noise, it's the read noise still. We are read noise limited, yeah? And yeah, this is still true for the I-band. So in all cases, the CMOS wins at this telescope. If we would put this at the 2.2 meter, I would have to repeat the exercise, and getting to larger focal lengths also means that you at some point would lose, because not only of field of view, but the large number of CMOS pixels. By the way, you can always bin, but it's just not on chip binning, it's binning on your computer, which is basically the same as adding the number of pixels as you do with DA of what anyhow. Good, so now let's move on to an experiment where we change the exposure time. Here we have a V band exposure of a 19th magnitude star, again 1 arcsecond seeing on a dark night. And this is when we go to 1 second. We are getting pretty much to the limit. You see just a faint signal on the CMOS side and a faint signal on the CCD. If you count the numbers with DA, then you get signal to noise, which is still a factor of 4 better for the CMOS. So this, please remember, for the read noise limited case, this camera always will win over a CCD. Even if I would say, if we could get to larger pixels for spectroscopy, this would be a very interesting point to make. And I've now repeated the exercise 10,000 times. Each dot is the result of such an experiment with differing exposure times. And you see here a plot of the number of detected photons in log scale over the effective exposure time, which is 100 seconds here and a tenth of a second there. And you see for, this is the CMOS camera, a nice, as you expect, linear plot with increasing noise towards the short exposure time end for the CMOS in the log-log plot. And the signal to noise of 10 point is at 1 second exposure time. And the detection limit that I would put at signal to noise 3 is at roughly 0.2 seconds exposure time. If I repeat the exercise for the CCD, please remember those locations of the green and the red circle. This looks quite different. So it's an order of magnitude worse. So this is where the high cadence comes in, where the CCD is outperformed by the QCMOS. And where I think at the 1 meter telescope, we really have a case. Now going to a somewhat fainter star, which is getting close to the sky brightness, 21.5 magnitudes. You probably can guess. Again, here now we have at, what is it, 10, 20, 30 seconds, signal noise 10, and detection limit at 10 seconds. This is really a faint star. And for the CCD, you're already at like 60 or 70 seconds where you reach the detection limit. So I hope this is convincing for pointing to an application at the 1 meter. And the nice thing is, technically, Stefan tells me that it's a plug and play thing because you have a C-mount. And whether it's really true, what needs to be accomplished, technically, we'll have to look at the mountain. This evening I will be there and tomorrow. But I hope that we really will quickly make an installation. And now this is what I would point back to you. Do we have science cases to do the interesting research that is, for now, I think, unique? I have not seen anyone else doing this kind of research on a ground-based telescope. This is what I was missing in the, sorry for the confusion. This is the 2 exposures that I mentioned of the asteroid taken from La Silla here and Paraná there, and the difference that was prompting me to suspect maybe, if you look here in the baseline between La Silla and Paraná, and then directly triangulating the distance of the asteroid, which is, what is it, 1.6 million kilometers, would be a nice application for solar system objects near. Stefan tells me that this is not interesting. So maybe there are other reasons to have 2 installations, but at any rate, as I told you already, the one on Tenerife will take at least half a year longer. Yeah. And whether it's a solid case to do something like that with ORCA-TWIN, yeah, that remains to be seen. But as I told you, I am intending to stir up a discussion and seek ideas to not only have the technical approach, but, and this is at the end of the day what we all want, to do the science. I have published a short research note on this, but I want to finish with recent information that I got from meetings. I attended a CMOS conference. Oh no, sorry, this is more recently from 2 weeks ago, a meeting in actually a course given by Teledyne on detectors in Munich. And here is what you see over the years, the US little survey strategic planning, where detectors always played a great role. But I wanted to stress time domain and multi-messenger astrophysics is something that is drawn out of the strategic process for the next decade to come. So it's on the high level becoming visible. And this is also true on the NASA report. This is difficult to read, but the two last item of the 4 is always single photon detection. This is then basically what I've shown you, this very low read noise QCMOS system, where actually there was another manufacturer in the US who has disappeared in the meantime. People say that Google has acquired this company. They also made a very low noise CMOS detector. And of that, I heard at another conference that I wanted to say initially, it was held in Toulouse about the CMOS technology. Here's a lady, a representative of Hamamatsu, who actually gave a 45 minutes tutorial on this very subject. And it turns out that the space community is extremely interested in this low noise detector. Also supported by a lady who's doing her PhD in Toulouse, Joanna Krinsky. And she also presented the other detector that has disappeared from the market. And you see, perhaps you can guess from the outline of the camera picture. This is creating a lot of attention. And again, for ground-based astronomy, this is, to my knowledge, not so much the case. We would have a good chance to be the first to bring it into business. And the last thing that I wanted to mention is I've just been made aware of something in the process of the strategy for what comes after the ELT at ESO. There is a call for ideas mentioned on the ESO website since a few weeks ago. Expanding Horizons is the title, where a bottom-up approach is seek to identify the next priority for a new facility, perhaps a new telescope. And I know of a group, and I have been contacted by a German representative, Thomas Kupfer in Hamburg, to propose the time domain telescope. I'm myself member of another initiative, the Wide Field Spectroscopic Telescope. Next week, I'm going to Garching to discuss with the science team the review of a white paper that was published already last year. So we are competing with it. But there are a few initiatives already on the market. Whatever the future of those perhaps proposals, the deadline will be next year, I believe. No, the call will be next year, and then a deadline a year after. Whatever the future will be, these slides that I don't ask you to read in detail, I can provide you with presentation with a number of science cases, is apparently a hot one. And what I've shown the first slides, transients, multi-messenger astrophysics, these are buzzwords that seem to be playing a role. And I will finish with the conceptual design. Jose Luis, you will remember, Jesus, making batteries of small telescopes to form a relatively affordable, large light collecting area. This is basically the bottom line of the time domain telescope idea that is in the process of emerging. I'm not saying that we should engage, but I remind you, Colorado is a fantastic place to put such telescopes. And we have discussed already this morning that maybe a small start could also motivate the concept of a similar kind, of which several in the world actually are being discussed, be in the future of Roth Observatory. So here I am with the conclusions. There are a number of topics that I've brought up already, which seem to make this case interesting for me. My colleague Katja Poppenheger, who is the new director at AIP, is engaged. Pedro, perhaps you also can attach to the MPORs and players. There may be many others, and I would like to stir up a discussion and from this community to see whether we can really not only make it a technical experiment, but a nice science application for Colorado. Thank you for your attention. I'm a bit over time.
Is there any question? Yes.
When are you going to do the first test? Tomorrow or today or?
Put this question to Jesus.
As soon as possible, as soon
Yeah.
as the camera is available.
The camera is available from now. We actually plan to fully characterize it in our laboratory in Görlitz, but we have two. So I would push to go with perhaps a quick experiment as soon as possible when it's realistic. You may have ongoing programs and we'll have to discuss this, but I would say yes, as soon as possible.
Well, I think that the potential use of this kind of detectors in astronomy is very big. Indeed, well, but first I would like to know something. You show the expected flags of the expected signal to noise of the detector,
Yeah.
according to the exposure time.
Mm-hmm.
Normally, these kind of fast frame rate detectors used to have an upper limit for the exposure time. What is the expected upper limit? Can you expose whatever you want, or is limited?
Of course, you have a full bell capacity limit,
Yeah.
after which the detector is nonlinear, and the full bell capacity of those small pixels is 7,000 electrons. So depending on the brightness of your object, there will be a natural limit of saturation. And the other limit that we want to actually measure in our lab is what happens with the read noise. Excuse me, the dark noise. The dark current does not play any role for those short exposures, but if you wanted to use it for, let's say, spectroscopy or exposures of 50 minutes, then you would like to know what's happening. And what the engineers tell me is that what is assumed to be dark noise is in reality actually luminescence, which can be controlled by switching off the transistor for long exposures. So this is still ongoing research and development. This is also motivating why we want to engage with Fraunhofer and the industry to have alternative routes of making, and I think Phil has pointed to this, the Chinese detectors to make large format CMOS. Teledyne is also going for this route, but we don't know what the future of Teledyne will be for Europe. So I flooded you with information. I hope you can circulate it in your community, because I really feel strongly that we need scientists who want to test it and actually make science. I'm not so sure about the community whether exoplanets is a big thing. So
I'm working on stellar occultations.
Yeah.
And we are moving to occultations of very faint stars. And then this technology helps us a lot. So far, we are using a commercial CMOS, which has a readout noise of 1 electron.
Yeah.
But this is a factor of 3 drop
Okay.
in readout noise. So we can go even fainter.
What is the typical magnitudes of the stars who occupy?
We typically observe 17th magnitude
No,
stars.
but you saw the example. I
Yeah.
mean, you could even go to 20th magnitude.
Yeah,
star.
recently we achieved one occultation of a 19.6 magnitude star, and we're pushing
Yeah.
further. So
So please, yeah.
yeah, and the number of stars that get occulted grows obviously. With the fainter the star, the more stars there are. So
Mhm.
this is an interesting topic. I put together an ERC application regarding to that, but it was not it was not granted.
Yeah.
So, but of course, the topic is very interesting for us.
So let's stay in touch.
Yeah.
Thank you.
I have two small technical questions. The dynamic range of the image we are getting is 8-bit, 12-bit, 14-bit,
It's a
16-bit,
16-bit.
16-bit,
Yeah.
true 16-bit.
Yeah.
Okay. And the second one, the software, the controlling, is it proprietary? Is there an API? If you, for example, want to develop some automatic scripting, so does
So it's typically distributed with a driver on Windows, and we have requested to have a Linux driver, which has actually been delivered, and we are actually in the process of getting an update.
Yeah.
So the company is open to respond to our requests.
So, and there's an SDK in software development kit if you want to program something by yourself, or just you can
Well,
use
for
the driver.
it's just a driver to read into the firmware. I'm very much doubtful that they will allow you to do anything at all.
Okay.
The classic problem. Yeah. You perhaps know also from the Telegram ASICs, etc. It's very hard to come by for those proprietary codes.
Okay. Thanks.
This is another reason why, no, when I pretend that we want to engage in a business that is really top end, and we have just a small team to start with, this is a process of 10, 15 years that we are looking into. But I know that ESO is very nervous about single source suppliers and the dependency. And then the points that you just mentioned, can you engage in the firmware code, and modify something on the readout, for example.
For
That
example, if you
would be-
want to have a region of interest, something
Yeah, that
like
is supported already.
that is already
Yeah.
supported. Okay.
Yeah.
Okay.
I can send you the data sheet if you're interested.
And what was the hardware connection? Is USB 3, Ethernet, or what?
No, it's a special cable that connects to a certain board that you plug into your computer. It has a length of 5 meters. I was a little bit concerned that it may be too short, but it now turns out it should be okay. Yeah.
And in the computer, you have a PCI card or something
Yeah,
like
it's
that?
a PCI card.
Okay. Okay. Thanks.
Maybe a comment according to this question, because Hamamatsu developed it not at all thinking of astronomical use. The formats are not astronomical at all, like not SER, not FITS, some special format, but it is possible to rewrite it. And also there are no FITS headers.
And the format is documented?
Yeah, it
There's
is
a document.
right?
So,
Yeah, but thank you for pointing this out. Yes, we will need a front end to provide it with proper filter
And
information.
Stella is working on that.
Yes.
especially for stellar occultations, for example, we need
Yeah.
a very the precise timestamp in the images.
Yeah,
That would be very rare. In general, for time domain astronomy.
very important.
So
And if you want to synchronize two telescopes, it would be even
yeah,
more
sure.
challenging.
Yeah.
Yeah, thank you for pointing out this. But I hear that you have on the telescope a clock that would allow to provide a timestamp that we can read and then code.
But how to input it is another.
Yeah, so we will need some R&D to really make it fully usable.
Yeah, especially if you have a proper image format.
Yeah.
But if it's documented, if they present it,
Yeah.
that's a big advantage. If it's not
So,
secret.
What my colleagues tell me is that the company seems to be open for requests of this sort. So if they discover that they may have a mark in astronomy, maybe they're even more open. The far that gets, I cannot predict.
Okay.
You showed us the transference limit rate is 0.45 terabit per second, right? For the full frame.
Yeah, that's for the full
It,
frame.
it should be some bottleneck to recording all the
Yes.
things. Yeah.
Our
hard
disk is
drives
full
or-
after a minute or so. Yeah, we will have to figure out how we deal with actually breaking down exposures such that you're not producing basically useless data that occupies your disk. And also a scheme how to have enough memory in the first place.
Are
That-
you using standard technologies for the transferring all the data to the computer? Yeah. Or you have special transference?
Well, I think this is
standards?
the same question.
Yeah.
There is just this interface board, this PCI card,
Yeah.
and then the
It's
code just
totally
stores
different,
on
yeah.
the disk, but without any astronomer useful information about
So
the
for
time.
now, it is not for the all standard users or how can I say amateurs, right? Just for the professionals. We
In
can
terms
say.
of price, probably.
Yeah.
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 It's very expensive, right? Yeah.
Yeah. I guess so.
So some amateurs has money.
But sorry, just a comment, but
Yeah.
as long as you can use a region of interest,
You can call it.
and then the amount of each image, the size of each image will be
Yeah.
increased, and that's
If you wanted to do differential photometry, then you may not want to use it. Or whether you can read multiple windows, I have to check. I can't tell you from the top of my head. But this is all, well, we'll have some experience after the first test and then identify a plan of what needs to be accomplished to make it useful for general purpose users.
you didn't mention the linearity. Did you measure that in your label?
We are
Yes.
intending to do this.
Okay.
The company claims that this camera has a huge advantage over EMCCDs with regard to the low count regime, but also coincidence losses, which is a problem for the EMCCDs. But we have not yet measured it. We are just starting. The lab that I was showing you is in. We're getting a test bench. We are getting an integrated sphere, light sources. It's not yet completed, but this is the first thing that we will do in the next months to come.
Okay.
That does not prevent us from putting the first test into operation.
Yeah, thanks, Martin, for this presentation. It's very interesting. It will make us think a lot about these science cases for this new instrument. But I was thinking about single photon detectors. These kind of detectors are now needed in several science cases and technological applications like quantum communications. Can this work as single photons detectors?
It is described in the data sheet, and I can send it to you. Actually, the major pool of customers is quantum computing and biology. Company was not aware that astronomers find an interest in that. Yeah, the answer is yes.
Thanks.
Just I'm curious. It's dedicated quantum computing. For what do I need such a camera for quantum computing?
So
Can
I'm a complete dummy. in
Me
this
too. That's
regime.
the reason
But
I'm
what
asking.
I've seen is that you can separate quantum states spatially.
Really?
So you get an image from waveguides.
Uh-huh.
And then you need, however, to be able to detect individual photons.
Okay. Thank you.
Let me say, since we seem to be exhausted, that I was very happy to hear that we can expect funding for MARCOT. And I wanted to thank my colleagues who have helped to make it possible. It is in the sense of what was shown in the slides, PDT, something in that direction. And I think we should use the precedents and be the first in those areas. And I'm super happy that we have astrophotonics now spread out and also being pursued here. When we had a visit from a colleague from CAHA in last summer. She proudly told us that CAHA is now engaging in astrophotonics. Yeah, you see, it's always nice to be on the forefront of something where most of your colleagues nod their heads and said, "Oh, this is why it's interesting." When we came up with PMAS in the 90s, my colleagues, even at my own institute, said, "What do you want to do with it?"
So, more questions? Okay, so thank you so much, Martin.
To you, the pleasure to be here always.
Thank you so much, everybody.